Once upon a time, in the extracellular space of Lungville, lived two superoxide radicals named Olivia and Ophelia. Olivia and Ophelia dreamed of attending the ball that was happening at the Cell Palace with all the other molecules, but unfortunately they were never invited. This was no surprise to them, because the palace does not allow any free radicals to enter. Olivia and Ophelia sat at home, upset, as they watched the other molecules head to the ball. They both wondered if they'll ever have the chance to go to attend a ball at the Cell Palace. Suddenly, out of nowhere, appeared their fairy SOD mother, the superoxide Dismutase 3 enzyme. She told Olivia and Ophelia not to worry, because they will have the opportunity to go tonight. The fairy SOD mother used her electrostatic looped wand that contained amino acids of lysine and arginine to guide Ophelia into her active site. Using her catalytically active zinc wing, she gave Ophelia the ability to donate an electron there, while the copper wing provided the fairy SOD mother to remain stable during the interaction. In return for the electron, 2 hydrogens were given back. Ophelia, who was previously a superoxide radical, has now become hydrogen peroxide. The fairy SOD mother then asked Olivia to come help release Ophelia from her active site. The superoxide radical rushed over, binding at the site, and Ophelia was set free. To thank Olivia, the fairy SOD mother provided her with an electron, turning Olivia from a superoxide radical into an oxygen molecule before being released. Olivia and Ophelia were now ready for the ball. They thanked the fairy SOD mother for this transformation as she left to go help other superoxide radicals in Lungville get ready for the ball. Shortly after, Olivia and Ophelia left to go to the ball with all the other molecules, and there they had a great time. The end. Let's quickly look at how the fairy SOD mother, the superoxide dismutase enzyme, looks like and functions. So the superoxide dismutase 3 enzyme contains 222 amino acids. This does not include the signal peptide. And the structure that is formed when folded is a homeotetramer. The signal peptide that is located at the N-terminal region of the enzyme contains 18 amino acids, and it allows the enzyme to be found in the extracellular space. For the signal peptide, we have 95 amino acids that have an alpha helical structure. In these 95 amino acids, residues 14 to 32 are responsible for the formation of the homeotetramer shape of the enzyme. And on residue 89, which is asparagine, glycosylation occurs. After this region, we have amino acid residues 96 to 193. This is known as the active domain, also referred to as the catalytic domain. The catalytic domain has a beta barrel structure, and it contains zinc and copper. Zinc is the catalytically active metal cofactor in the enzyme, and it binds to amino acid residues 113, 121, and 124, all that are histidine. Zinc is also binded to the amino acid asparic acid, which is located on residue 127. Copper, on the other hand, acts as an enzyme stability agent and binds to 4 histidine amino acids. These can be found on residues 96, 98, 113, and 163. An electrostatic loop created by lysine on residue 136 and arginine on 144 allows the superoxide radical to find the active site. There, the radical is able to donate an electron to zinc, allowing it to transform into hydrogen peroxide. This creates a metal peroxide complex. After, a secondary oxygen radical is needed in order to release hydrogen peroxide and restore the active site. The secondary radical gets released as molecular oxygen. In the active domain, there are also 2 intrachain disulfide bonds that happen between cysteines on amino acid residues 107 and 89, along with 45 to 190. At the end of the chain, we have residues 194 to 222 at the C-terminal region. These are highly hydrophilic and have a alpha helix structure. They allow for interactions with a number of different ligands. In particular, amino acids 210 to 222 allow for interactions with heparin, and in residue 219, we can also see an interchain disulfide bond that allows for interactions with other molecules. Now you know how the superoxide radicals get dealt with in the extracellular space.